Welcome to the Introduction to Computer Lecture Series, CSN at Problem Solving Tools. My name is Engineer Sahon Kuro. I am Doctor. So in this series, we're going to be introducing us to the different out there. By now, you already have been from go through what a problem is, and then the different techniques regarding chapter. We're going to be looking at that we use to interactive in the sense that we are going to be working with real-time examples so that we can be able to comprehend most of the things that we are talking about. The very first tool that we'll look at is abstraction. The very first tool that I'll be looking at here is abstraction. Now, abstraction is a problem-solving tool, and it's a very powerful problem-solving tool that allows us to simplify complex systems, concepts, or programs by focusing on the essential details while ignoring the unnecessary complexities. It involves creating a high-level representation or model that captures the important aspects of the program at hand, and we are going to be looking at some ways of being. The first is managing complexity. The second is identifying patterns. The third is creating models. The fourth is information hiding. The fifth is encouraging usability, enabling scalability, and facilitating communication. Now, looking at managing inherently complex, and it involves numerous variables, dependencies, and interactions. So abstraction helps in breaking down the problem into smaller or more manageable parts, allowing us to analyze and then solve them independently. Let's take, for example, that simulates traffic flow. It's developing software that simulates traffic in the city. The problem at hand is inherently complex. That's to develop the software for the traffic flow in the city, and it involves numerous variables such as the vehicle types, the road conditions, the traffic lights, and driver behavior. So to manage this complexity, you can apply abstractions by breaking down the problem into smaller and more manageable parts. Now, breaking it down, we have 4 parts that we are broken it down into. We have the abstraction of road network, we have abstraction of vehicle behavior, we have abstraction of traffic control, and we have abstraction of driver behavior. Combining all of them together will now give us the software application. So the first one, which is the abstraction of road network. Instead of considering every individual road and intersections in the city, you can abstract the road network as a graph. Each road segment becomes a node, and the connections between them represent the intersections. So these abstractions allow you to focus on the connectivity and flow of vehicles rather than specific details of each road. So when you're writing your code, you are now focusing on the connectivity and the flow of vehicles rather than the specific details of each road. The second part of which is the abstraction of vehicle behavior. Yes. Rather than simulating each vehicle individually, you can abstract the behavior of different vehicle types. Yeah, the behavior of different vehicle types. For instance, you can categorize vehicles into cars, buses, and trucks, and define general characteristics such as acceleration, maximum speed, and braking behavior. Now, this abstraction allows you to model the overall traffic flow without really dealing with every individual vehicle. So you understand how we are going about it now. And the third one is the abstraction of traffic control. Now, instead of simulating every traffic light in the city, you can abstract the traffic control system as a set of rules. Yes, a set of rules or procedures. For example, you can define the timing pattern for traffic lights based on the traffic volume of the day. Yeah, you can decide to have it that way. So this abstraction allows you to simulate traffic flow under different scenarios without getting into the specifics of each intersection that before. Then the next is the abstraction for driver behavior, which is the last actually. So instead of you modeling each driver's decision-making process, you can abstract driver behavior by defining the probabilistic rules. For example, you can assume that drivers will slow down if they encounter congestion or follow a certain distance from the vehicle in front. Now, this abstraction allows you to capture the overall traffic patterns without considering the actions of individual drivers to become so cumbersome for you. So by allowing these abstractions, you can simplify the problem of simulating traffic flow in the city. Now, each abstraction focuses on specific aspects of the problem while ignoring the unnecessary details. Each of these abstractions, we have for the road network, we have for the vehicle, traffic control, and driver behavior. They take you towards the necessary aspect of it, the specific aspect of the problem, while ignoring other issues. You understand? It's making it easier to analyze and solve the problem in a more manageable way. Now, additionally, these abstractions allow for modularity, as different components of the simulation can be developed independently and integrated seamlessly. So you can decide to look at that for the road network, develop it separately, look at the one for vehicle behavior, do that separately, traffic control and driver behavior all separately. Then you integrate everything together to come up with the software application. Now, overall, managing complexity through abstractions help in breaking down complex problems into more manageable parts, just as we have done in this example. Now, it enables effective problem solving and solution development. So you can see. Now, looking at the second part, we've talked about managing complexity. The second part is identifying patterns. Abstractions allow us to recognize common patterns or structures that exist across different problems. By abstracting away specific details, we can focus on the underlying similarities and then develop general solutions that can be applied to a wide range of instances. Let's take for example, let's consider the problem of detecting spam emails in an email system. Spam emails in an email system. So spam emails are unwanted messages that are sent in bulk and often contain deceptive or malicious content. To identify spam emails, we can use abstractions to recognize pattern in the email content and metadata. So here's how we can do it with this example. We also have four parts here in this case. We have the abstraction of textual pattern, abstraction of sender reputation, abstraction of metadata, and abstraction of user feedback. Now, coming back to the abstraction of textual pattern, by analyzing a large data set of emails, we can abstract common textual patterns that are indicative of spam content. For example, we may observe that spam emails often contain words like free, discount, winner, or use excessive capitalization and exclamation marks. These patterns can be abstracted into rules or regular expressions that capture the common feature of spam emails. So the second abstraction is the abstraction of sender reputation. Another pattern to consider is the reputation of the email sender. Abstraction can be applied to identify common characteristics of known spam senders. For instance, certain email documents or IP addresses might be associated with a high volume of spam. By abstracting these patterns, we can develop algorithms or models that assign a reputation score to each sender, aiding a spam detector. Now, the third abstraction is the abstraction of metadata. which is metadata such as the email headers can provide valuable information for identifying spam patterns. So abstraction can help in recognizing patterns in metadata such as suspicious email routing, inconsistent timestamps, or unusual email formats. So by abstracting these patterns, we can build filters or algorithms that leverage metadata to flag potential spam emails. That's that about that. And the last one, which is the abstraction of user feedback. User feedbacks play a crucial role in spam detection. By abstracting user actions and feedback, such as marking emails or as spam, that's marking emails as spam, or moving them to the junk folder, we can identify patterns that indicate spam. These patterns can be used to train machine learning models that learn from user feedback to improve spam detection accuracy. By identifying these patterns, through abstraction, we can develop generalized solution for spam detection. So instead of relying on specific keywords or sender names, we can build algorithms or machine learning models that generalizes the identified patterns across a large number of emails. This approach enables the system to adapt and detect new spam patterns that may emerge over time. So overall, abstractions help in recognizing common patterns in spam emails, allowing us to develop generalized solutions that effectively identify and filter out spam from email system. This abstraction-based approach improves the accuracy and efficiency of spam detection, while also enabling the system to adapt to new spam patterns as they emerge. Yeah. Now, another way you can also use abstraction is by creating models. Abstraction involves creating simplified models or real-world system or processes. These models capture the essential characteristics and behavior of the system, allowing us to analyze and understand it better. Models can be mathematical, they can be conceptual, or visual representations that provides insights, facility problem solving. Let's take, for example, let's consider the problem of predicting housing price based on various features such as the location, the size, the number of bedrooms, and other factors. So to create a model for housing and price prediction, we can apply abstraction to simplify the problem and develop a mathematical model. And here's how we can go about that. The first that we'll do is feature selection. First, we need to abstract the problem by selecting the relevant features that influences housing pricing. For instance, we might consider features such as square footage, number of bedrooms and bathrooms, location, proximity to amenities, and so on. So by abstracting away irrelevant or less significant features, we focus on the key factors affecting housing pricing. Now, the second aspect is data collection. Once we have identified the relevant features that we need, we will collect a data set that includes housing examples along with the corresponding prices and chosen features. This data set serves as the basics for creating our model. And when we have done that, we now do what they call the model representation. This step is to create a mathematical model that relates the selected features to the housing prices. One commonly used model is the multilinear regression. In this abstraction, we assume a linear relationship between the features and the housing prices, and the model estimates the coefficient of each of these features to predict the prices. The model can be represented as, let's say, the price, which is equal to BO, which is the coefficient without any feature, and B1 times feature 1 plus B2 times feature 2 down to Bn times feature n. Now, where BO and B1, B2 are the coefficients to be estimated, those are the coefficients to be estimated in a linear regression. Now, what do we do next is that we will now train the model. To estimate the coefficient of the model, we need to train, we need a training phase rather. Now, during training, the model is represented with the data set and it adjusts to the coefficient to minimize the differences or the difference between the predicted prices and the actual price in the data set. This process involves optimization techniques like least square or graded descent to find the optimal values for the coefficient. Now, after doing that, we now do what they call the model evaluation. After training the model, we need to be after training the model needs. After training, the model needs to be evaluated to assess its predictive performance. We can use techniques like cross-validation or hold-out validation to measure how well the model generalizes to new unseen data. The evaluation helps us understand the accuracy and reliability of the model's prediction. And lastly, we now have what they call the model deployment. So once we are satisfied with the performance of the model, we can deploy it. We can deploy it to make predictions on new unseen housing examples. So by imputing the relevant features of a house into the model, it will provide an estimated price based on the learning coefficients. So by creating this mathematical model, we have abstracted the problem of predicting house pricing into a set of features, and coefficients. So the model provides a significant representation of the relationship between the features and the prices, enabling us to make predictions and gain insights into the housing market. So in overall terms, rather, summarizing this, I have to go back, is that creating models through abstractions allows us to represent complex real-world problems, just as the pricing we just talked about in a simplified and mathematical form. This models provides a structured framework for analyzing and solving problems, making predictions, and supporting decision-making processes. So that will now take us, we've looked at the three types. Now we take us to the next types of abstraction, which is information hiding. Abstraction helps in hiding unnecessary details or implementation complexities, exposing only the relevant information to users or other components. Now, this enables modularity, as different parts of a system can interact through well-defined interfaces without needing to know the internal workings of each component. As usual, let us look at an example of an abstraction in hiding information. Let us consider the development of a web application for an online shopping platform. The application consists of various components such as user authentication, product catalog, shopping cart, and payment processing. To ensure modularity and maintainability, information hiding through abstraction can be employed. One is the user authentication that is listed above. That one component is one important aspect of it all. So it involves managing user credentials, validating user information, and ensuring secure access to the application. By abstracting the authentication functionality into a separate model of all class, the internal implementation details such as encryption algorithms and database schemas can be hidden. The rest of the application only needs to interact with authentication model through well-defined interfaces. such as login and registration methods, without needing to know the intricacies of the authentication process. Now, the second thing is the product catalog, which is the product. Now, the product catalog is another critical component of the application that manages the inventory, product information, and search functionality by abstracting the product catalog, the details of the underlying database structure, identifying algorithms and search algorithms can be hidden from other parts of the application, just like we said previously. The rest of the application can interact with product catalog through interfaces that provides access to product details, search results, and inventory management methods without needing to know the internal workings of the catalog. Now, the third part, which is in information hiding, will be shopping cart. Now, the shopping cart functionality allows users to add items, update quantities, and proceed to checkout. By abstracting the shopping cart model, the implementation details such as the data storage, session management, data storage, session management, and cart calculations can be hidden. Yes, they all can be hidden. The rest of the applications interact with shopping cart module through interfaces that provide methods for adding items, updating quantities, and retrieving cart information without needing to be aware of some specific data or structure or algorithms used. Now, finally, in our example is the payment process. We're trying to hide information using abstraction. So the payment process component handles secure transactions and integrates with external payment gateway. By abstracting the payment process model, the complexity of the payment protocols, encryption mechanisms, and communication protocols can be hidden. The rest of the application interacts with payments processing modules through interfaces that handle the initiation, verification, and completion of transactions without needing to understand the underlying payment mechanism in details. So by applying information hiding through abstraction, each component of the web application encapsulates its internal implementation details, exposing only the necessary interface to interact with other components. This modular design approach promotes code reusability, maintainability, and ease of development. Additionally, it allows for independent updates or replacement of independent components without affecting the functionality of the entire application. So in summary, information hiding through abstraction enables the creation of modular components in a software system by abstracting away internal details such as algorithms, data structures, and implementation specifics. The components provides well-defined interfaces for interaction while maintaining the necessary encapsulation. So this abstraction promotes the modularity, reduces dependencies, and enhances the overall robustness and maintainability of the system. So after looking at that, now let's look at the fifth way of using abstraction to solve problems, which is encouraging reusability. By abstracting common features or functionalities into reusable components, we can save time and effort in problem solving. This abstraction serve us as building blocks that can be applied across different contexts, promoting efficient and effective problem solving. Let's take, for example, an abstraction that encourages reusability. Let's consider a scenario where you are developing a library of utility functions for mathematical calculations. Abstraction can be applied to create reusable abstractions that can be utilized across different mathematical operations. Here's how it can be done. The first is abstraction of basic operation, abstraction of specialized functions, abstraction of data structures, abstraction of algorithm. We're going to look at the first. The first, which says that the abstraction of basic operations. Identify common mathematical operations that are frequently used across different calculations, such as addition, subtraction, multiplication, and division. So abstract these operations into reusable functions, such as classes that can be easily incorporated into different contexts. For example, you can create a function called add that takes two numbers as input and returns their sum. Or you can do the same thing with subtract. Then, after doing that, you now look at abstraction of specialized functions. Identify specialized mathematical functions that may be required in specific scenarios, such as trigonometry functions, sine, cosine, and tangent functions, logarithmic functions, or statistical functions. Abstract these functions into reusable components that can be easily integrated into various calculations. For instance, you created a class called trigonometry that provides a method for calculating sine, cosine, and target. You can do that. That will now also move us to the abstraction of data structures. Now, considering the data structure that are commonly used in mathematical operations, such as vectors, matrices, or complex numbers, abstract these data structures into reusable classes or modules that encapsulate the necessary functionalities and the operations. So these abstractions enables the reuse of these structures into various mathematical calculations. For example, you can create a class called vector that provides method for vector addition, dot product, and normalization. Okay, so normalization. So that will now take us to abstraction of algorithms. In this abstraction, you identify commonly used mathematical algorithms such as sorting or numeric optimization algorithms. Abstract these algorithms into reusable components that can be applied to different data sets or problem domains. For example, you can create a model called sorting that provides functions for various sorting algorithms like bubble sort, merge sort, or quick sort. By abstracting these mathematical operations, functions, data structures, and algorithms, you create reusable components that can be easily incorporated into different projects or scenarios. Developers can leverage this abstraction by simply import or including the relevant modules or classes, reducing the need to implement the same functionality from scratch. For instance, other developers are working on different projects. Other developers are working on working on different projects can utilize the add functions. That's if other sorry, I was a bit distracted. Using the add functions for utility library to perform addition operations without having to write the code themselves. Similarly, they can use the specialized functions. They can use specialized functions from trigonometry classes or the data structures from the vector classes to perform calculations in their specific domains. The reusability achieved through abstraction saves time and effort. It promotes consistency and enhances code's maintainability. So developers can focus on the higher level programming solving aspect by leveraging these reusable abstractions, accelerating the development process and then reducing the likelihood of introducing errors. So in all, abstraction encourages reusability by creating modular and encapsulated components that can be easily integrated into different contexts, promoting efficient and effective software development. You understand? Software development. Now, the next is enabling scalability. Abstraction plays a very important role in scaling solutions. By abstracting essential elements of a problem, we can define solutions that can handle large data sets, more complex scenarios, or increased workloads. This scalability is achieved by focusing on fundamental aspects while accommodating the necessary flexibility. For example, let us consider a social media platform that allows users to post, share, and interact with content. As the platform grows, the user base increases. Scalability now becomes crucial to handle the increasing load and maintain performance. So abstraction plays a significant role in achieving scalability. And here's how we are going to do it. The first is abstraction of user management. To handle a growing number of users, abstractions can be applied to the user management system. So instead of having a single monolithic database table to store all user data, the system can be abstracted to distribute user information across multiple database servers using techniques like shading or partitioning. This abstraction allows for horizontal scaling by adding more servers and distributing the user load efficiently. Another way is abstraction of content storage. As the amount of user-generated content grows, storing and retrieving content efficiently becomes essential. So abstraction can be applied to content storage system by using techniques like object storage or distribution file system by abstracting away the underlying storage infrastructure. So the system can scale horizontally by adding more storage nodes and handling increased content volume without affecting the performance. The next abstraction is abstraction of caching. Now, caching is a crucial component to improve system performance and handle scalability. By abstracting the caching layer, the system can utilize distributed caching mechanisms such as this thing they call memcache or Redis. Now, this abstraction allows for caching layer to be scaled horizontally by adding more cache servers, reducing load on the back-end systems, and improving response times. Now, that will now take us to abstraction of micro services. Microservices architecture provides scalability benefits by breaking down the system into smaller independent services. Each microservice can be abstracted to focus on a specific function such as user authentication, content moderation, or notifications. This abstraction enables each microservice to scale independently by deploying multiple instances of the service and load balancing the incoming request. Then we'll now look at abstraction of messaging queues. As the system grows, processing tasks asynchronously becomes crucial to handle spikes in traffic and ensure responsiveness. Abstraction can be applied to the message queue system when tasks are decoupled from the main application flow. By using a message queue service like RabbitMQ or Apache Kafka, the system can scale horizontally by adding more message tasks concurrently, something like that. So by employing these abstractions, the social media platform can achieve independent scaling of different components, ensuring that the system can handle increased user load, content volumes, and processing requirements. So the modular nature of these abstractions also allows for easy management and deployment of the system, as individual components can be scaled or upgraded without affecting the entire system. So in all, abstraction enables scalability by breaking down the system into modular components, allowing for horizontal scaling, efficient resource utilization, and improved performance as the system grows. This approach ensures that the software system can handle increasing demands while maintaining reliability and responsiveness. Now, the last but not the least is the facilitating abstraction in facilitating communication. Abstraction helps in conveying complex ideas or concepts more simply and understandably. It allows people to communicate and collaborate effectively by providing a shared mental model or representation of the problem, which adds in problem-solving discussion and decision-making processes. Let's take an example. Imagine a software development team working on a complex project with multiple modules and components. Effective communication among this team is crucial for understanding requirements, coordinating tasks, and collaborating on the project. So abstraction can be applied to facilitate communication by providing clear and concise representations of complex concepts. So here's an example of how it can be done. Abstraction of the system architecture. When discussing, help simplify the communication by presenting high-level diagrams or models. This abstraction provides an overall of the system's structure, showing the major components, their interactions, and the flow of data or information. By abstracting away implementation details, team members can focus on understanding the system's architecture, how different components interact without getting overwhelmed by unnecessary technical details. The next is abstraction of the interfaces. In a project with multiple modules or components, abstractions can be applied to define clear interfaces between different parts of the system. These interfaces act as contracts specifying how different components should communicate, with each other. So by abstracting the communication protocols and methods through well-defined interfaces, team members can easily understand the expected inputs, outputs, and behaviors of different components, enabling effective collaboration and integration, which moves us to abstraction of user stories or use cases. When discussing specific features or functionalities, abstraction can be used to create user stories or use cases that capture the essence of the user interactions and system behavior. User stories abstract the requirements from the perspective of the end user, focusing on their goals, actions, and expected outcomes. So by using user stories, team members can communicate and understand desired functionalities and behaviors without getting caught up in technical implementation details. So the next will be abstraction of the APIs. In projects involving integration with external services or modules, abstraction can be applied through well-defined APIs, which is the application programming interface. APIs abstract the underlying implementation details and provides a simplified way for different components of the system to communicate and exchange data. By abstracting the complexity of communication protocols and data functions, APIs facilitate effective communication and integration between different systems or modules. Now, it takes us now to, I think, the last, which is the abstraction of documentation. Documentation is an essential communication tool in software development, whether you like it or not. So abstraction can be applied in documentation to present information in a clear and concise manner. Instead of overwhelming team members with technical details, documentation can focus on abstracting the most important concepts, functionalities, and user guidelines. So this allows team members to quickly grasp the key information and communicate effectively without getting lost in excessive details. So by applying abstraction in these different communication aspects, team members can have a shared understanding of the project requirements and desired behaviors. So abstraction helps in simplifying complex concepts, highlighting the essential information, and enabling effective communication among team members with different roles and expertise. So in overall, abstraction facilitates communication by providing clear and concise representation of complex concepts, allowing team members to understand and collaborate effectively. It helps in creating a common language and shared understanding, promoting better coordination and enhancing overall productivity of the software development. So in summary, abstraction is a problem-solving tool that allows us to simplify and manage complexity, identify patterns, create create models, hide on necessary details, encourage reusability, enable scalability, and facilitate communication. So by abstracting away the non-essential aspects, we can focus on core elements of the problem and advise more effective solutions. Thank you for being in this first section. In the second lecture, we are going to be looking at algorithms. Thank you very much.